Hello everyone. In today's session, we'll be going through the resource management, that is radio resource management, also short termed as RRM, for mobile broadband D2D connection. So in this section, the key aspect related to D2D RRM, both from a state of the art and future resource perspective, are covered. The focus is on mobile broadband D2D scenarios, that is scenarios with typically low mobility, where offloading of the cellular network, enhancement of the system capacity, and improvement of the user experience in terms of reduced latency and increased data rate plays a dominant role. The focus will be on in-band unrelated D2D, in which D2D communication uses the same spectrum and resources as cellular communication. This section is structured as follows. Firstly, a brief overview of RRM technique for mobile broadband will be discussed. Then, it is followed by some of the most significant RRM and system design challenges which is to be solved. In order to make D2D a native and efficient technology in 5G system will be discussed. So that means to say we'll be posing some challenges and we'll be going through what are the challenges exactly the developer is facing, or the current situation, in the current situation the developer will be facing when D2D is integrated to the 5G technology. Now, what do you mean by RRM? RRM is nothing but radio resource management. Radio resource management means the radio frequency which is available has to be managed such a way that the coexistence occurs between the connection between the base station and the connection between the device to device. So what are the few questions? Few questions will be there. So the questions will be we'll be going through the question, and also we'll be trying to find the answer for the question, and also two algorithms will be there. So in the algorithm we will be going through the uplink and downlink algorithm. Okay, and how the interference is happening between the device to device, and from device to a base station, and from one base station to another base station in today's session. Next, RRM technique for mobile broadband D2D. In addition of the D2D layer as an underlay to cellular network, poses new challenges in terms of interference management in comparison with traditional cellular communication. These challenges comes from the reuse of resource between cellular and D2D users, which creates intra-cell interference. Therefore, in order to exploit the benefit of D2D communication and achieve an improved system performance over the baseline cellular-only system, careful resource management should be utilized or should be used, and should be taken into account both the cellular and the D2D user. Okay, so in addition, what it says here is, in addition to the D2D layer as an underlay to the cellular network, which poses a new challenge in terms of interference management, which we have already gone through the interference. What are the interference which occurs when D2D is integrated with 5G, and also the challenges will come from the reuse of resource between cellular and D2D users, reuse of the radio frequency resource between the cellular and the D2D users, and again, in order to exploit the benefit of D2D communication and to achieve an improved system performance over the baseline cellular only system, which is a 4G system, careful resource management will be taken into account for both cellular and D2D user. Okay. Next, along RRM algorithm and techniques for D2D underlay communication can be classified depending on the optimization metric and the tool used to achieve that optimized or improved performance. The most common objective or optimization metrics for of RRM algorithm and techniques are: first is spectral efficiency, second is power minimization, and third minimization in performance, and with quality of service constraints. So these are the main objectives of an optimization or optimization matrix of an RRM algorithm. So what are the main objectives? First is spectral efficiency, next is power minimization, and performance with quality of service constraint. Okay, now the basic toolbox of available RRM technique commonly agreed in the literature uses mode selection, resource allocation, and power control. So these are the three toolboxes which will be available in RRM, and which is very important. So we will be discussing each and every toolbox in detail. Okay. Now the first one is mode selection, which is also short termed as MOS. Okay. Several factors influence the mode selection decision, such as distance between the devices, path loss and shadowing, interference condition, network load, etc., and the time scale on which MOS should be operated. A MOS decision can be made before or after the D2D link is established. That is, mode selection can also happen before or even after the device to device link is established while operating on the low time scale. Example, based on distance or large scale channel parameters. Okay. Further, mode selection can be done on a faster time scale based on changing interference condition, which is coupled with resource allocation phase. Okay, so this is nothing but selection of a mode. Okay, the selection of the mode depends on what? The selection of the mode depends on the path loss, interference condition, network load, and the distance between the devices. Mode selection decision can be made, which can be made before or after the link is established. Okay, so this is the first mode selection. Then is resource allocation, that is also short termed as REA. So these are the toolbox of RRM. So REA determines which particular time and frequency resource should be assigned to each D2D pair and cellular link. Okay, resource allocation algorithm can be broadly classified according to the degree of network control, that is centralized versus distributed, and the degree of coordination between cells, that is single cell and versus the multi-cell. So the resource allocation, again, you guys have got a basic idea about resource allocation, mode selection, interference issues, right? So resource allocation is nothing but the allocation of usage of the resources which is available in a more proper way. Okay, the resources here is nothing but either it can be an uplink and downlink system, or either it can be a radio resource management, radio resource which can be managed. So this can be managed either by centralized version or via distributed version, and also by single cell or from the versus the multiple cell. So this is the resource allocation. Next is power control. This is PC. In addition to mode selection, resource allocation, and power control, this is one of the major or most important technique which we have to deal with. Okay. The focus is mostly on limiting the interference from D2D to the cellular transmission in order to improve the overall system performance while ensuring that the cellular user experience is not integrated or not degraded. Sorry. Okay, plays and very interference both intercell and intercell, which result from underlay D2D operation. So the power control should be provided during the transmission from during the connection either from D2D or from D to the base station. Next, RRM and system design for D2D. So these are the three toolbox which we have gone through. Toolbox for RRM technique, which will mode selection, resource allocation, and power control. Okay. The next is RRM and system design. The system design which we have designed for the D2D, that is device to device communication. Okay. Now, complementing evolved legacy standards. Legacy standards are nothing but the old systems or the 4G and 3G with non-backward compatible radio interface. Non-backward means once the 5G is introduced, it cannot be used for a lower versions. Okay, and 5G will allow designing a radio technology that natively and efficiently supports D2D from the onset. Some of the general challenges to support D2D on 5G system with its broad scope of use cases and scenarios are highlighted. The focus here is to specifically address some of the fundamental RRM and system design questions which is to be answered for efficient support of mobile broadband D2D. For instance, first is how valuable is the usage of D2D across multiple cells, and does this justify the additional coordination and signaling burden which will be introduced? Now understand the question here. How valuable is the usage of D2D across multiple cells? And does Thus justify the additional coordination which is required and signaling burden which will be introduced. Okay, now we will see what exactly is the solution for this, or what exactly is the answer for this. Now, enabling inter-cell D2D requires some kind of basic conflict prevention of RRM decisions between the serving base station of the device involved in D2D communication, even if not targeting optimally coordinated resource allocations. Okay, it could be the case that in half duplex system, that is in 5G, one base station schedules one of its assigned D2D user for uplink transmission, while the other base station schedules a direct D2D transmission towards the same user. So this will violate the half duplex constraint. Okay, sorry. So what happens here is enabling inter-cell D2D. Enabling inter-cell D2D requires some kind of basic conflict prevention. So first is the conflict prevention of the radio resource management. Okay. So what is the conflict? So one, for example, we can see here as in a half duplex system, one base station is trying to give an uplink transmission to a user, while the another base station or another device is going to connect to a device-to-device transmission. So that is violating the uh, violating the half duplex model, or is there is a system conflict. So how to overcome this? So solution to prevent this issue may include exchange of scheduling information between the base stations either via centralized or through coordination entity. Second is protocol level solution that can orchestrate the order of transmission. Then third is simply disabling intercell D2D. Now if we simply disable intercell D2D, what happens is again there is no use, or there is no use of integrating D2D in a 5G system. Okay, so what we can do here is we can give a protocol level solution. In the protocol level solution, what happens is protocols will be assigned either for the cellular network or for the D2D. So whichever has the highest protocol level or the highest priority, that will be accepted by the device. Okay, next solution is, and one more solution is one more solution will be coordination between the base stations. Okay, the coordination between the base stations either can be through centralized or through direct coordination between the two base stations. So by this we can avoid the conflict. Okay, now the next challenging question which we'll be posing is how should mode selection between D2D communication and device infrastructure device be performed, and on how much time scale should this be conducted. Okay, now how should mode selection, okay, that is MOS, between D2D communication and device infrastructure device is nothing but device with base station, be performed, and on what time or which time scale should this be conducted. So we'll see now. The possibility to make use of fast, instantaneous signal to interference and noise ratio based mode selection against a simpler path loss based slow mode selection will have a major impact on the protocol stack design. Okay, it is needed to carefully evaluate the trade-off between achievable gains, complexities, and signaling overhead. Next question which will be posed is instantaneous channel state information, that CSI, of all potentially interfering cellular and D2D link needed for scheduling purpose. Okay. Now first is, or is the statistical CSI knowledge enough? Statistical is nothing but the numbers. So as we can see here, the channel gain among D2D pair is required. The channel gain between D2D transmitter and cellular user interface is required. Channel gain between cellular transmitter and D2D receivers are required. Okay, so we will see what exactly it does. In general, D2D communication requires information on the channel gain of D2D pair, that is quality of the direct link. Next, the channel gain among D2D pairs will be required. The channel gain between D2D transmitters and cellular user interface will be required. Channel gain between cellular transmitters and D2D receivers is required. In addition to the CSI information of cellular only system, all this information will be required. Okay, the exchange of such extra channel information can be an intolerable overhead to the system, if instantaneous CSI feedback is needed. Okay. Next, 5G D2D RRM concept, which is an example we'll be providing. Okay. In this section, an example of 5G D2D RRM concept in the concept of flexible TDD, that is time division duplexing air interfaces described. The seamless integration of D2D in the flexible uplink or downlink or TTD frame structure is presented, and the joint multi-cell D2D and cellular resource allocation is explained for the case of centralized and decentralized schedulers. Afterwards, adequate mode selection scheme for D2D are analyzed. Finally, some of performance numbers showing the gain of D2D with flexible TDD over fixed TDD and centralized or decentralized scheduling are provided. The performance and implementation implication of two mode selection algorithm that operate on different time scales are also compared. So we will see what exactly we are comparing. Now, first and foremost is the flexible uplink and downlink time division duplexing concept for D2D. The uplink and downlink dynamic time division duplexing concept for D2D is based on MIMO, OFDMA air interface. It is orthogonal frequency division multiple access. The TDD optimized radio has a flexible frame structure that enables fast time division duplexing access and fully flexible uplink and downlink switching. In addition to support for non-conventional type of communication such as D2D and self-backhauling, each cell can flexibly switch the data frame to UL, that is uplink or downlink, within a scheduling slot based on short-term traffic requirements without requiring clustered TDD. This is self-explanatory. That is the flexible uplink and downlink concept. So flexible uplink and downlink concept is nothing but it uses first MIMO OFDMA air interface. First thing. Second thing, the time division duplexing optimized radio has a flexible frame structure. Okay, the flexible frame structure actually enables the time division duplexing access to fully flexible the uplink and downlink switching. Okay, so either the same can be used for uplink as well as for the downlink. So that is what the flexible uplink and downlink concept is. So each cell can flexibly switch the data frame to uplink or downlink within a scheduling slot based on short-term traffic requirements. So however the traffic requirement is there, the same frame or frame structure can be used for both the uplink and the downlink conditions. Okay. Next, the D2D communication is natively integrated into the flexible time division duplexing frame by considering the D2D user in addition to the cellular user. Okay, the scheduler decides among uplink, downlink, and D2D with simultaneous reuse of resource between cellular and D2D user, which is allowed for that cell, taking into account both favorable transmission condition and user fairness. Next, there is a figure here which illustrates the challenge and opportunities presented by multi-cell D2D communication in scenarios with flexible time division duplexing. The focus is on specific scheduling slot and resource block, assuming that resource reuse between D2D and cellular use is allowed. Okay, now this is an example here. Now you can see that there are the dotted lines are the interference lines and the thicker lines are the signals. So if we take one example here, that is the first one. So we can see that base station 1 and user interface 1, they both are connected. So there is no, they both are connected, and user interface 1 and user interface 2 is not in close proximity with each other. So when there is no close proximity between these two devices, then there will be no D2D connection which happens here. So the first one, base station and the user interface, has no interference whatsoever. So this is one cell and this is one cell. Now if you go for user interface 2, so user interface 2 has a close proximity with user interface 3. So a D2D connection is established between user interface 2 to user interface 3. Whereas there is also an interference with the base station. Okay, so the base station is also interfering with user interface D2D, user interface 2. Sorry. Next, if we see this base station 1 and base station 2. They both are having an interference with each other because they are very close to each other. Okay. Next is if we go for user interface 4, these were inside the cell. Now we are going outside the cell. The user interface 4 is in connection with user interface 5. That is because they both are in close proximity and device to device D2D connection is established for uplink and downlink. Now, but user interface 4 has an interference from base station 1 as well as the user interface 3. Okay, so we can sum up here, that is downlink to uplink interference from base station 2 to base station 1, base station 2 to base station 1. Okay, downlink to D2D interference, from base station 2 to user interface 5. You can see this here. Next, D2D to uplink interference generated by D2D transmitters like user interface 2, user interface 4 towards base station 1. Okay, so you can see this, it sums up the entire session which we have gone through. That is coexistence, interference with each other, and reuse concepts. The same radio resource which is connected from user interface to a base station is reused for device to device connection. Okay, so this is an example which is very much important for understanding. Now in the next session we will be talking about decentralized and centralized schedulers. So what do you mean by decentralized and centralized schedulers? Centralized, that is coordinated, or decentralized, which is uncoordinated schedulers. Okay, now resource allocation approaches are considered, leading to two different architectures. That is, in the decentralized case, each cell performs its own resource scheduling decision. In the centralized case, the channel quality information from the user is further forwarded by the respective small cells to a centralized entity in the network. Okay, so in decentralized and centralized schedulers will be used. The scheduler centralized is nothing but coordinated, and decentralized is nothing but uncoordinated resource allocation. Resource simply means either radio frequency or any kind of resource which is available for the connection. Okay, now there are two different architectures. One is for centralized scheduling architecture, one is for decentralized scheduling architecture. So in scheduling architecture, different architecture. In the decentralized case, each cell, okay, performs its own resource scheduling decision. It only whatever schedule it has to make, it will make on its own, depending on the resource which is available. But in the centralized case, this is not the condition. That is the coordinated case. Okay, the channel quality information from the user is further forwarded by the respective small cells to a centralized entity in the network. Okay, example, a macro cell which performs coordinated scheduling decision. Next, the optimization matrix is delay weighted sum rate maximization for each resource block in a cell, okay, or a group of cells, considering all cellular, that is uplink and downlink and D2D link in that cell or a group of cells respectively. The scheduling potential of each link, either cellular or D2D, depends on the achievable data rate on that link. Okay, and the packet buffer delay. So the optimization metric is delay weighted sum rate maximization. So that is delay, and which is weighted because of the weighted means nothing but not weighting. Which is weighted means the priority which is given to it. Okay, the priority which is given to it. So the sum rate maximization for each resource block in a cell. Okay, that is in a decentralized case, or a group of cell in a centralized case will be considered, considering all cellular links, that is uplink, downlink and D2D link in that cell or group of cells respectively. The scheduling potential of each link, either cellular or D2D, depends on the achievable data rate on that link. Okay, which is based on again SINR, that is signal to noise ratio, estimation from interference condition in the previous scheduling slot, the packet buffer delay, and to provide user fairness in terms of the delay. Now, simply nothing but what happens here is what I mean the schedulers. The schedulers are the device which is used for scheduling of any kind of resources. which is available resources. So schedulers are of two types: centralized and decentralized scheduler. Centralized and decentralized scheduler. Okay, so that is what we'll be going through now. Now, scheduler centralized is coordinated, that is in the group of cell. Decentralized is uncoordinated, that is each cell. So each cell, how we will be optimizing the scheduling. Scheduling will be optimized based on delay as well as the weightage of the system. Okay, considering all the cellular network, that is uplink, downlink, and D2D link in that particular cell is active. Okay, the scheduler decides for each available resource block which link should be made use of it, either an uplink, downlink, or D2D links. Okay, possibly with resource you reuse between cellular and D2D communication based on brute force search of the configuration that provides the highest delay weighted sum rate out of all the possible combinations. Okay, the scheduler decides for each available resource block which link should be made use of it. Okay, should make use of it. Either the link is uplink, downlink, or D2D links. Okay, how it is made use of, how it is scheduled, or how it decides. It decides on a brute force search. What do you mean by brute force search? Brute force search means extensive searching, just direct searching of the configuration that provides the highest delay weighted sum rate out of all the possible combinations. Okay. In the decentralized case, the scheduling decisions are made for each cell independently, whereas in the centralized case, they are made jointly for a group of cells, including all the possible scheduling links in the cluster. Okay, for a decentralized case, the scheduling decisions are made for each cell independently. Okay, whereas in a centralized case, they are made jointly for a group of cells, including all the possible schedulable links in the cluster. Okay, it should be noted that intercell D2D is also supported in the decentralized case by means of simple scheduling conflict resolution mechanism that ensures the fulfillment of the half duplex constraint in the system. Now, it is worth mentioning that performance of the brute force scheme is to be seen as an upper bound on the performance of any particular scheduling algorithm, and that the scheduler assumes instantaneous knowledge of all channel gains between the cellular and the D2D user. Okay, now mode selection. Mode selection. Mode selection is especially relevant when the separation distance between the users, that is with traffic to be exchanged, increases. Okay, that is which mode has to be selected. When the separation between users increases. In that case, the routing of the D2D traffic through the infrastructure may be more efficient than making use of the direct link between the devices. Okay, when the distance increases, okay, the mode which can be used will be the direct link between the infrastructure, that is between the base station, that will be more efficient than a D2D device. Okay, hence it's important to investigate the adequate time scale to perform mode selection between D2D and DID communication. Okay, here the choice is between fast, that is based on instantaneous SINR information, and slow time scale based on large scale channel conditions. Clearly, conducting fast mode selection would imply that the decision is executed at the MAC layer itself, whereas in the slow mode selection case, the decision would be performed at the PDPC or the RRC layer. In fact, the following forms of mode selections are considered. The first one is direct D2D only and indirect D2D only. Direct D2D only is nothing but all D2D traffic is served through direct links between the devices. Reuse of resource block is allowed between cellular and D2D users. The indirect D2D only, that is device infrastructure device. All D2D traffic is routed through the infrastructure. That is, infrastructure is nothing but the base station. A D2D communication involves two hops, that is a uplink transmission and a subsequent downlink transmission. no direct D2D is allowed. So two modes are used, that is mode selection, to either fast mode selection or slow mode selection. Okay, that is between the D2D and the DID communication. This is the mode. So as and when the distance between two devices increases, it is better to use a DID communication, that is a connection between the base station and the device rather than D2D. So for slow selection, it will be, the decision will be performed in the RRC layer, whereas for the fast decision, fast mode selection, the decision can be made in the MAT layer. So usually two different types of mode selections are involved. One is direct D2D only, second one is indirect D2D. Now direct D2D is served through direct link between the devices. Okay, indirect is served through infrastructure, that is through indirect method, through going to the base station, from base station to the uplink transmission, from the base station to the device using uplink transmission and downlink transmission. Okay. Next, path loss based slow mode selection, which is the third one. So first is direct D2D, second is indirect D2D, third is path loss D2D, next is fast mode selection. So there are four mode selections which will be utilized, which will be used during the selection of the mode from D2D to DID. The first one is direct D2D only, second one is indirect D2D only, third one is path loss based slow mode selection, fourth is fast mode selection. Now path loss based slow mode selection. Now D2D traffic is routed through the infrastructure when the path loss towards the serving base station and a bias is lower than the path loss of the corresponding direct D2D link. The bias favors direct D2D communication over DID due to the inherent advantage of direct D2D mode selection is done before resource allocation itself. That is path loss based slow mode selection. Okay, that is, there is a path loss which is because there is a connection between D2D, because there is connection between the user interface with the infrastructure. So obviously the infrastructure will be kilometers away from the device. So obviously, when there is an uplink or downlink, so there will be a path loss towards the serving base station. Okay, and a bias is slower than the path loss of the corresponding direct D2D link. Okay, so that is what is path loss based slow mode selection. Next, fast mode selection. D2D traffic is routed through the infrastructure or through the corresponding direct D2D link, depending on the comparison of the estimated SINR condition between the link that connects the D2D user interface to the infrastructure and direct D2D link. Okay, now this is the fast mode selection. The D2D traffic is routed through the infrastructure or through the corresponding direct D2D link, depending on the comparison of estimated signal to noise ratio condition between the link that connects the D2D user interface to the infrastructure and direct D2D link also. Okay, this calculation is done as per scheduling slot based on interference condition in the previous slot. Okay, so this is the fast mode selection. So next is performance analysis. This performance analysis will be going through in the next session. Okay, hope you have understood the current mode selection technique, centralized and decentralized schedulers, and the example for 5G or DTD, D2D RRM concepts. Okay, see you in the next class. Thank you.